Hello. Once again, we pursue our lessons. In our next lecture, we spoke about the classification of functions, whether they are algebraic, and we said the meaning exactly of an algebraic function. One where you can calculate f of x using the 5 arithmetic or algebraic operations, a finite number of terms. And also there are some transcendental functions like the exponential, logarithmic, the trigonometric, etc. But actually we didn't expose them in detail. So in this lecture we shall not classify them, but study these functions and see their properties, because we shall be using them all the time later on. Now, the subject of basic functions here, we shall be speaking about the power function, and the power function is the function of rule x to the power n, where x is a variable, a real variable here, and n could be anything, could be real, could be real rational, could be irrational, could be integer, etc., and whether positive or negative. And amazingly, this power function, although it seems to be the easiest, it's not really so, because there are so many varieties in this power function. And then the exponential function, and this is very often used in economics, where it studies or it shows decays of phenomena and growth of phenomena, growth, for example, of the economy, or periods of recession, etc. So they are very well expressed using this function. And then there is the trigonometric functions, and trigonometric functions, which are the sine and cosine. Seldom really we find them in economics, but it's important to know them, because even students at school, they come across them. Why? Because trigonometric function, they have the property of being cycling or periodic, and in very all the time, or often we encounter in a variety of fields, not especially economics, periods in which the function, for example, grows and then decays, etc. And like, for example, you have a period of inflation, then you have, and the economy, for example, is growing, and then you have other period of depression. And these cyclic behaviors of a function, for example, it can be really. There was a scientist who was contemporary to Napoleon, and this scientist had a theory saying that any cyclic or periodic function can be expressed in the form of a series of trigonometric functions. And so these trigonometric functions really are worth exposing in order to give the student the background of how a cyclic behavior can be dealt with. And then we shall speak of hyperbolic functions, and these are related to the exponential functions. Now, first, the power function. The power function has the rule f, which maps x to x to the power n. Now, x to the power n can be a very simple thing, like when n is integer. When n is integer, like you have, for example, a straight line, y is equal to x. This is the equation of a straight line passing by the origin. This is when n is equal to 1. But when n is equal to 2, we met this before when we spoke about parabolas. This is a parabola open from above. Y is equal to x squared, a parabola open from above, and the range starts from 0 to infinity. And then you have x cubed. X cubed, y is equal to x cubed, resemble very much the letter S in Latin or in English, and this y is equal to x cubed is a function that has a range and domain R. Now, these are the easiest, really, when n is integer. Now, when n is integer, the power function x to the power n comes into or gets involved or be one element in a series called polynomials. So, for example, f of x, the first line above here in the slide here, this is called a polynomial in which the coefficients can be really integer, can be just real, rational, or irrational, and this is called a polynomial of power n. Now, the simplest is when n is equal to 1, and you get this is the equation of a straight line. And this straight line is very simply, you met it before, where the intersects with the y-axis at value b, and the slope is equal to 8. Now, this is a second degree equation, and it's quadratic equation. X squared plus bx plus c for all values of a, b, and c. Now, if a is positive, then if a is positive, you get the equation open from above, and it's called concave upwards. Whereas if A is negative, then you get something like this. Now, in order to graph this function, x squared plus bx plus c, what you do is that you can take A outside and you get x plus b over A. Here you get b over A plus c over A square x. And then you can express it in this form, x plus b over twice A all square plus c over A minus b square over 4a square, because you have to come back to the same form there. Now this, if this is negative, then it can go to the left-hand side, to the right-hand side, I'm sorry, and you have a root. And you know before the expression for the root is equal to minus b over 2a plus or minus the square root, which is called the discriminant. So you must have that in order to have a real root, then you must have that b square over 4a square minus c over a must be greater than 0, or that b square minus 4ac is greater than 0. Then you have a root. And then this, if you have a root, then your graph would look like this, or would look like this. If you have a root, if you don't have a root. But here to graph this or to draw it, it's simple. Why? Because we said before in one of the previous lessons that you start always to draw any graph by the simplest. Here the simplest is x squared. So you start by x squared. But this x squared here, instead of x squared, it has to move b over twice a either to the right or to the left. So if b over twice a is positive, then you shift left. Whereas if it is negative, you shift right. And then you add to the y this value here, which you either go up or go down, provided that this is a negative, then you have a root. And if it is completely positive, then you don't have a root, and the value of y is always positive, because here or a negative, depending on the sign of x, because actually the sign can be expressed outside. In other words, if you have, for example, minus x squared, so you get minus a outside, and it means that you revert your graph. So this is called second degree equation, and you have to know how to draw it. This one is a third degree equation, and it's a polynomial also. Usually when you seek to find the roots, usually the roots, either you have one real root or you have three real roots. Now we shall not go into detail for this, because it needs that you can't have two real roots. Otherwise, the one that is left is complex, and complex they don't exist alone roots, because the coefficient a, b, and c and d are real, and therefore it has to have either one or three real roots. Now, when n is integer, so you see the varieties of the power function. And now when n is negative, you get, for example, here this is 1 over x. So 1 over x is an odd function with symmetric about the origin, 1 over x, this one and this one here. For x positive, it's this one, x negative, this one. Whereas when you have n is equal to 2, so you have 1 over x squared, so you have an asymptote at x equal to 0, and it goes to infinity. These are the two here, 1 over x squared. Of course, here the previous function, the domain is always r, whereas here the domain is r except the point x equal to 0. Now this function here appears as one of the ingredients, one of the elements of a called rational function. This is a rational function. Of course, if all coefficients disappear except, for example, 1 over x, then you get the previous function, or 1 over x squared. But in general, you have something like this, and this is a polynomial over a polynomial, and the equation, this equation here, or f of y is equal to f of x, the domain is r, except you have to exclude the roots of the denominator. Now here, when you have, for example, n is equal to half, so where n is equal to half, you have square root of x, for example. This is the domain is x greater or equal to 0. But when you have n is equal to third, like y is equal to, for example, x to the power third, then here the domain is equal to r and the range is equal to r, because it exists in both sides. So, but in general, so actually when I speak about the domain, I say also in general the domain is from 0 to infinity. And here as well, the domain is from 0 to infinity. You got, for example, x to the power 5 over 3. Here, it's an even function, x to the power 2 over 3. It's even, of course. And sometimes it only exists on the right-hand side, like, for example, x to the power 3 over 2. Then for x negative does not exist. It's complex, and therefore, in general, similar to the previous one, the domain is for all values of x greater than or equal to 0. Now, you may also have the power is rational, but it is negative. And here, the domain, in general, it's for x greater than 0 only, like x to the power minus 2 over 3, or x to the power minus 3 over 2. This exists only for x greater than 0. And this is why we always say that the domain of this function, in general, is for x greater than 0. And then all these functions that we exposed here are functions that are algebraic. Why the algebraic? Because we use algebraic operations to calculate them. When, for example, you want to calculate 1 over x to the power 7 over 3, what you do, you divide. This is one algebraic equation. X power 3 is an algebraic equation, and or x to the power 7, and then you extract the third root. So you are doing algebraic manipulation. Whereas here, for example, this is the only case in which the function is not algebraic. Like, for example, x to the power n, where n is pi or a square root of 2, because we don't know how really to extract x to the power pi. You have to use logarithm, and therefore you have to use a transcendental function in order to calculate this value. And therefore, for any irrational, the function which is x to the power n is not an algebraic function. Now you have exponential functions. No, exponential functions are associated with either usually it's a constant greater than 0 raised to the power x. And we saw before in the classification of function, this is not an algebraic function because here x could be anything, could be square root of 2, could be half, could be, since it runs over the real line. So actually this function is not algebraic. And usually you find it under 3 situations only, for where a is equal to either 2, like, for example, in computer studies, for example, where you deal with Boolean algebra and 1 or 0, the two possibilities, and 10 to the power x also, and 10 to the power x because you are counting, you have 10 fingers, and then you have e to the power x, which is the most reputed, and this e we saw before, it's called the Euler number raised to the power x, and this function here is the solution of an equation, like the derivative is equal to the same function. And actually it's only function in mathematics almost that I may say yes, the only function in mathematics in which the derivative is equal to the same value of the function. And it's you find these kind of functions associated with phenomena of growth and decay. Now here it is. This is the exponential function. Of course, you can have a is equal to 1. 1 to the power x is equal to 1. This is a straight line. Y is equal to 1. Here, of course, the more you raise the power, or the more you have an a, big A, 10 to the power x, of course, greater than a to 2 to the power x for x positive, and smaller for x negative. Now this one, a to the power a is equal to 0.5. You have 0.5 to the power x, which is equal to 1 over 2 to the power x. In other words, 2 to the power minus x. So either you say it's 0.5 to the power x or 2 to the power minus x. Of course, it's decaying. So this function is monotonic decreasing for a here, like 0.5, and it's monotonic increasing for a is equal to e or 2 or 10, etc. And it's constant for a is equal to 1. Now, the property of exponentials, you know the theory of indices, a to the x plus y is equal to a to the power x times a to the power y, or when you subtract the exponents, or when you raise them, these are known from school. Now, the exponential function, as a matter of fact, is one function that appears in economics when you deal with compound interest. When you deal with compound interest, for example, you put your money in the bank with an annual rate R, and then you leave it n years. So what you get at the end of the first year, you get your money times 1 plus r, which is the interest. But when you put it another year, it's compound interest, you get 1 plus r to the power n. square 2 when n is equal to 2, when n is equal to 3, etc. So as a matter of fact, here you have a, which is 1 plus r raised to the power n, and this gives you the money that you, or the money that you have at the end. This is your capital raised to p times 1 plus r to the power n. Of course, your benefit or what you gained, you subtract from this p to get the benefit that you, or the interest that you received at the end. Here it is. For example, you start with p at n equals 0 at the beginning of your at the fiscal year, and then you put your you deposit your money in the bank, and then of course if you have no interest, then you end up whatever number of years you leave your money in the bank, you get the same capital. But if you have a certain interest, like for example 3% or 5%, the more you have interest, the more you have. This is an exponential function, of course, where n is here discrete. It's not really like a to the power x, but it's almost the same. I mean, you can connect them together to have a kind of exponential function. Now, trigonometric functions, as I said, are worth exposing. Why? Because, as I said before, they are responsible for the study of all phenomena that have a cyclic behavior. Many things in our life are cyclic, and like for example, I myself, I cycle. Sometimes my mood is not well. Sometimes I'm depressed. Sometimes my serotonin is high, so I'm happy, etc. So there are cycles in life. The moon itself is a full moon, then there's the crescent, etc. So the economy itself, you have periods of growth and periods of recession. So if this continues for a period of time, you can analyze this through trigonometric functions. And this is why it's worth exposing and studying this function. Now, a trigonometric function, you have 6 of them, and they have no units, they are ratios. Here you have, and this is what they call circular functions, because you can associate them with a circle. Here you have a circle of radius 1, you can take any radius, and then you can take any point P and project them point P on the radius, the horizontal radius here, and this distance you call it A, and the other one, the height, you call it B, so the sine becomes B divided by 1. Whereas the cosine is A divided by 1. In other words, the sine is the opposite by the hypotenuse, and the cosine is the adjacent divided by hypotenuse. And whereas the tangent is B over A. And this is why always sine is less than 1, because B is always less than 1 and A is less than 1. So sine theta and cosine theta are always, they vary between 1 and minus 1. Why minus 1? Because the sine here sometimes B is positive, sometimes is negative. For example, if the theta exists in the 4 quadrant here, B is negative, so the sine is negative. So it's only positive when B is positive. In other words, the sine is positive in the first and second quadrant. Whereas the cosine is, because the cosine is A divided by A, so A is positive either in the first or fourth, so you get the cosine positive in the first and fourth quadrant, etc. Whereas the tan, it can vary depending on B and A. Now, cosine, sine, and cosine, these functions, they always have a range between -1 and 1, whereas the tangent, it can go to infinity. Why? Because here, B, the maximum value of B is 1. And same thing for A. The reciprocal of the sine is called the cosecant, whereas the reciprocal of the cosine is called the secant, and the tangent is called the cotangent. Here is the sine function. This is a sine function where you have here this called the period. In other words, every 2 pi it repeats itself. So it has a period of 2 pi. The function itself, I can represent it in this form. The range of the function varies always between -1 and 1, because the sine is B over 1, and B is the radius is less than 1. So always you get a sine which is always less than 1 and greater than -1. So the range always varies. In other words, there is no such sine function is equal to 3, for example. You cannot use the calculator. If they give you sine function is equal to 3 and try to obtain x, it's not possible, because the sine never equals 3. It has to vary between -1 and 1. And same thing for the cosine as well. This is the cosine. So the cosine, it varies between, it is cyclic also. It has a period of 2 pi, but it's in phase by 90 degrees with the sine. So at 0 there, it's 0. The sine is 0, whereas here, the cosine of 0 is equal to 1. But whereas for for the range, it's same thing. It's like the sine function. It varies between -1 and 1. So the sine and the cosine function both have a domain R and a region in the closed interval between -1 and 1. And both of them are out of phase by 90 degrees. Now, suppose, for example, you have, they want you to study, for example, the parity of a function like sine x over x. So the parity of sine x over x here, you have to check it using the test that we have spoken about before. What you do is that you substitute x for minus x, and then you see what's the value of this function, f of minus x. So here, you substitute x for minus x, you get sine minus x over minus x. And I told you before that the sine in the second quadrant, in the fourth quadrant is negative, so sine of minus x is equal to minus sine x. So the minus sign cancels out to obtain sine x over x. In other words, f of minus x divided by f of minus x is equal to sine x over x, which is f of x. So here it means that the function is even. And as you see here, this function is even, which is symmetric about the y-axis. Now, suppose you want, for example, someone asks you what is the upper and lower bounds for f in the interval from 0 to pi. They want to obtain the maximum value and the minimum value of such expression, 4 sine x minus 2 cosine x. How do you do this? Usually, we use absolute values to deal with situations like this. So what you do, you know very well that the sine function varies between -1 and 1. In other words, the modulus of sine is less than or equal to 1. Whereas the modulus of the cosine, same thing for all values of x. So what you do, you use the inequality that we have seen in our second lecture. You have modulus a plus b is less than or equal to modulus a plus modulus b. And therefore, the modulus of f of x is equal to the modulus of this expression here. But the modulus of this here, a minus b, is less than the modulus of this, the first expression, plus the modulus of the second expression. Now, the modulus of the first expression here, ab, is the modulus of 4, which is 4, times the modulus of sine x, plus 2 times the modulus of cosine 2x. Now, whether you use sine or cosine or sine 2x or cosine 6x, always the modulus is less than 1. So you substitute here, this is by 1 and this is by 1, and you got modulus f of x is equal to 6. So this means what? This means that modulus of f of x is less than 6, or that f of x lies between 6 and minus 6. Now, is there any value of x at which f of x is equal to 6? We don't know. This we don't know. But we are sure that the modulus cannot exceed 6. So but it cannot exceed 6 and it cannot exceed 7. And it could be equal to 5 only. We don't know this, but this is called an upper bound. So this is an upper bound of the expression for modulus f of x. So the function has an upper bound. Now, you can have, here is the function. When we draw the graph of this function here, we discover something nice about it, is that there is a point at which the function reaches 6. So we call this value least upper bound for this function. Why? Because if you have something which is less than 1,000, for example, it may be less than 1,000 and it may be less than 500. But if it reaches a value of 500, we call this 500 least upper bound, because the least, this is the smallest value, and still it's an upper bound. In other words, there is no such lower upper bound for this function. But here it's not only a least upper bound, but it's always a maximum. Why? Because there exists a value pi by 2, at which when you substitute in the rule here, you get 4 sine pi by 2, which is 1, cosine pi by 2 times 2 cosine pi, which is minus 1, so you get 4 plus 2 is equal to 6. So in fact, this is the maximum value of this function, because there exists a point at which the function reaches a value of 6. So we call this the maximum value of this function in the interval from 0 to 2 pi. Still, suppose the same function, you say investigate the upper bound and lower bound for this function, but you exclude the point pi by 2. I'm only just assuming that the same problem being expressed otherwise by stating that you can let us investigate the same function, but exclude the point pi by 2. So in which case then pi by 2 does not lie in the domain of the function, because we exclude it. But yet the function has an upper bound of 6. And at the point pi by 2, here, if we substitute here, you get 6. But 6 does not lie in the range of the function. Neither pi by 2 lie in the domain of the function. But still 6, we call 6, in which case it's a least upper bound. So here 6 is the least upper bound of the function if you exclude the point pi by 2, whereas it's maximum here when you insert the pi by 2 or let it be an element in the domain of the function. This is the time function. Well, the time function is different than the sine and cosine. It is a naughty function because it can go to infinity. It has asymptotes, infinite number of asymptotes at pi by 2, at minus 3, and minus pi by 2. It can go also to infinity from the right hand side or from the left hand side. When x is less than pi by 2, it goes to infinity. When x is more than pi by 2, a little bit more than pi by 2, it goes to minus infinity. So it has infinite number of asymptotes at pi by 2, at minus pi by 2, at 3 pi by 2, etc. And all the values you have an asymptote. So what we say, the function is tan y is equal to an x. The domain is R, except at those points at which x is equal to 2n plus 1 times pi by 2. In other words, pi by 2 and 1 is equal to minus 1, pi by 2 minus pi by 2, 3 pi by 2 minus 3 pi by 2, etc. And you go on, and this is your time function. Obtain the domain, this is a problem, obtain the domain of f if f is given in the form of 10x over x. Now this is, we know 10x, that it has an infinite number of asymptotes, and the domain, you have to exclude these values to n plus 1 pi by 2, but also you have to exclude the 0. Why? Because you divide by 0, and you said before, we cannot divide by 0, so when you find x in the denominator, it means that you have to exclude the roots of the denominator, so the single root here, x equal to 0. So we said the domain of this function is the set of real variables, except you have to exclude the roots of 10x at which 10x, those at which 10x have an asymptote, or they go to infinity, and at the same time you have to exclude the value of x equal to 0. Now these are the opposite of the sine function. They are called the Cossack function. This is 1 over sine. So of course, since sine range from minus 1 to 1, and the cosec is equal to cosecant is 1 over sine, so it must range from what? From 1 to infinity. You divide, so if you have an interval from minus 1 to 1, and you have 1 over this interval, so it means that you start by 1, and you have a 0, so you go to infinity. So the range of this function here, the domain, again, is R, except at the point at which the sign is 0, of course. So you exclude 0, pi, 2 pi, etc., while the range is from 1 to infinity and from minus to infinity to till minus 1. In other words, the union of these two intervals. And same thing for the cosec, and same thing for the cotan. Now, suppose you wish to write this is sine x. We said before, you have here 2 pi, this is the period. Suppose you have sine 2x, what will happen? It means that here you increase the speed by which the sine goes to 0. Instead of going to 0 to pi, it goes to 0 at pi by 2. So you have something like this. And this actually we can exemplify easily using here. This is an applet here, again designed at Cairo University by a young man called Bassem. What he did is that he tried to exemplify how the sine function, when you increase the frequency, you get a different graph. Now, when you increase a, as I said, you get double the frequency, because the frequency, if you call the frequency f, and since the number of cycles, each cycle takes 2 pi, so the number of radians, it becomes 2 pi f, and the sine function becomes sine omega t, or sine twice pi t. Of course, when you increase a more, you have, this is when x a equal to 3, or when x is equal to 4. So you have 4 times in which the function annihilates or come back to the value 0. Instead of only at 0 and pi and 2 pi, it becomes 0 at pi by 4, etc., and pi by 2, etc. Of course, the cosec, which we just seen, are the opposite one. These are the cosec of the function. Now, this function here, which is the sine function, you will see directly the maximum of the sine is 1 and the minimum is -1. So whereas the sine function has domain R and range from -1 to 1, same thing for the sine. The Cossack, on the contrary, has a domain is equal to R, except at those points at which the sine function cancels or are equal to 0. So it's 0 and pi and 2 pi, etc. And again, at which it has an asymptote, and the range of which lies from -infinity to -1 and from 1 till infinity. Now, for the trigonometric identities, these are important. Here, I tell my students, students usually are, they found it difficult. They are frightened from the identities. They found them so many. But I tell them all the time that you have only got 3. This one is from Pythagoras, sine squared x plus cosine squared is equal to 1. In other words, you never need to memorize more than these 3 inequalities. This is the first one. And then you have sine x plus y is equal to sine x cosine y plus cosine x sine y. And cosine x plus y is cosine x cosine y minus sine x sine y. Now, suppose, for example, you need a different or a new relation of sine to x. What you can do is just put here y is equal to x. So you get sine to x is equal to sine x cosine x plus cosine x sine x, which is twice sine x cosine x. Again, suppose, for example, you need to find sine square. You can use here. You put y is equal to x, so you get cosine square. Cosine to x is equal to cosine square x, because minus sine square x. And then you substitute cosine square x by 1 minus sine square. So you have a relation between sine square x and cosine 2x. For example, if you want to prove that sine to the power 4 is equal to this, what you can do, it's easy. What you can do is that you start by sine square x, which is equal to the last identity, half minus half cosine 2x. You raise it to the power, and then you substitute here again cosine square x by double the period, and you get your expression at the end. So it's not complicated. Sometimes you need, for example, to draw the graph of cosine square x. Well, you have 2 possibilities. Either you draw the graph of x and then you square it, or better, you can substitute cosine square x by half plus half cosine 2x. Here, cosine 2x is the same curve like the cosine, except that the frequency has been doubled. And we saw before that when you have y added up half, then you raised the graph by half. So this is the way. You have to find easy ways of drawing graphs. Again, here, for example, you have e to the minus x sine x. E to the minus x sine x, it's easy because you have here, you have, for example, here e to the sine x, e to the x, e to the minus x, and you have sine x. So what you have something like this. Here e to the minus x, and like this. In other words, you have a graph which is comprised between e to the x and e to the minus x, and it alternates as well with the same period of sine x. Now we have also a hyperbolic function. The hyperbolic functions are they extracted from the exponential functions. They are only defined. They have nothing to do with the sine and cosine. But because they have same properties. In other words, sometimes you find, for example, that sine hyperbolic of twice x is equal to twice sine hyperbolic of x cosine hyperbolic of x. And this is why they give them the same symbols, but they added an h symbol meaning hyperbolic. So this is the sine hyperbolic function, and it looks like this. And it's equal to e to the x minus e to the minus x over 2. This is the cosine hyperbolic, and it's an even function. And this is the expression for it, and this is the tan hyperbolic function, and it has a region. The domain is R, and the range is the open interval from -1 to 1. Whereas here the domain is R, and here also the domain of R. Here the range of R, and here the range from 1 till infinity. These are the inverse, the opposite of these hyperbolic functions. We cannot. There is no need to study them because you can find them in anywhere, or you can investigate them using the previous functions. And again, these are hyperbolic identities. The hyperbolic identities are the same exactly like the previous ones. There, for example, we have sine square x plus cosine square x is equal to 1. Here we have cosine hyperbolic square x minus sine hyperbolic square x is equal to 1. In fact, as I said, the hyperbolic identities have nothing to do with the trigonometric ones, but because they share the same, they resemble them very much in the relation, so they used them and they add them the letter h, and this letter h means something with conic section, because the conic sections, when it's circular, it provides, or this is the source of the trigonometric functions, whereas the hyperbolic curve, there it's circle, here it's the hyperbolic curve which provides the source of these hyperbolic functions. And they have very similar identities like the previous one, and this is why we kept the same symbols except that we added the letter h. So before we investigated, you remember this is a circle, equation of a circle, x squared plus y squared is equal to 1. If you want to transform this Cartesian implicit function into a parametric function, what you do, you can just there put x is equal to cosine t and y is equal to sine t. So here, this is the value, this is the point, which is the order pair cosine t sine t, and this is a parametric equation. If you cancel out t from both, you get this one. What is x? This is the projection of this radius on the real axis, you get x, whereas the opposite is equal to y, because actually x is equal to the radius 1 times cosine the angle, and the height is equal to sine the angle. And the t here represents what? Represents the angle which this radius subtends or makes with the x-axis. So we see now the relationship between the trigonometric functions and the circular and the circle, or the representation, how you deal with implicit functions of this sort, like of circles, and how can be transformed into a parametric form using the cosine and the sine. And therefore, we say that these functions, the cosine or sine, instead of relating them with the triangle, you can relate them very well with the circle. Whereas if you have a hyperbola, and we said before, what are the hyperbola? The hyperbola is one of the conic sections, and when you cut a circular cone, right cone, by a plane, you either get an ellipse, a circle, or hyperbola. If you cut it such that it's orthogonal to the base, you get a hyperbola. This is a hyperbola. The equation of the hyperbola, here's the equation of the hyperbola. When it is plus, you got a circle, but when it is minus, you get a hyperbola. The hyperbola here, this is the point 1 and 0. And if you take any point, then you can represent, instead of sine and cosine, you represent it by cosine hyperbolic and sine hyperbolic. Why? Because we said before, from the identities of the hyperbolic function, that cosine hyperbolic square minus sine hyperbolic square is equal to 1. And therefore, you can, instead of representing the hyperbola in this form, you can represent it in the parametric form, and therefore any point will take the order pair cosine hyperbolic and sine hyperbolic. So there, t in the circular functions represent the angle which makes the radius with the x-axis in the circle, whereas here t represent double this area of this small little bit looking like a triangle. This area here, double of this area is t. So we saw now we investigated or exposed many of the basic functions. We spoke about the power function, and amazingly, the power function has so many varieties. And then we dwelled on the trigonometric functions, and the hyperbolic functions also. They are useful. Of course, most in economics usually we don't see much of the trigonometric function, but as I said before, sometimes you do, and it's a shame that students of any discipline would not know these functions. And I said that you can study any cyclic behavior using these functions. The hyperbolic functions also, they are not something new. They are extracted from the exponential functions, and the exponential functions, they can lead to, and because these hyperbolic functions, they look very much similar in relationships like the trigonometric functions. So what we do is that we give them the letter h because they are extracted from or related to the hyperbola. So I wish to just to remind you, as we came to the end of the lecture, first of all, I would like to thank you very much for your attention. And until we meet again in our next lecture, I wish you good luck. And I wish to remind you that all these lectures, what are the preceding ones and the one that we're going to teach later on. They're all uploaded to the site of the Uninuttuno platform. You find them, and all of them are there, and you can use them, and you can sign in to study or to listen to them. Thank you very much.